These articles are trained on pairing the headline of each article with its first sentence to create an input summary pair. The result obtained from this model gives us a Roach 1 score of 21.18. What is a Roach metric? A Roach metric is recall-oriented understudy for gesting evaluation metric, which compares an automatically produced summary or translation against a reference or a set of preferences or human-generated summary for translation. The framework that they used in this research paper is the torch, and these are some of the mathematics of attention-based model. The most important thing is the scoring function. The scoring function gives us the scoring function tells us that the generated word is a function of the contextual output, which is the previous words and all the words in the input. And the conclusion is that a neural attention-based model for abstractive summarization, which is based on the recent developments in machine translation, this combines probabilistic model with generating algorithm, which produces accurate abstractive summaries. And the next steps are improving the grammaticality of the summaries. Now let's proceed to modeling. In the modeling approach, we obtain a CNN Daily Mail dataset from the Decathlon NLP. The datasets contain 90K plus 175K stories from these websites, and each file is stored as .stories file, as we can see from this picture. Each story contains articles and summary text. These articles are combined together and split into train, test, and validation stories. Then each story in each set is tokenized using Stanford NLP and converted into vectors, tokenized and converted into text files to analyze them, to read them, and then they are converted into binary files. The parameters that we used in our model are hidden dimensions for LSTM, which is 256, embedded dimensions of 128, the batch size of 16, the maximum encoder steps, the maximum number of words that can be used during one time step are 400, maximum decoder steps of 100, which tells us that the length of the summary will be 100, a beam size of 4, which tells us that the decoding will be performed based on 4 nearest neighbors for our predicted word, the vocabulary size of 50,000. Creating a sequence-to-sequence model. The first stage is single-layer bidirectional LSTM model. A single-layer bidirectional LSTM model encoder uses two LSTM cells, one for abstracting information from the past and one for extracting information from the future. This gives us a better understanding of the context. Adding a decoder. This uses an LSTM cell too. Then we add an attention model. An attention model tells us what is the most relevant data to memorize. It takes the decoder is a word output fed as input to the generator to generate a next model until we have a complete headline. The output word waits over each input word to determine how much attention to be paid to the input word. Running the model. The model trains on the training dataset. This gives us model checkpoints for each epoch and stores the best results in it. These checkpoints are utilized for evaluation of the validation dataset, and again the best results are stored as checkpoints. This is further used in testing and obtaining Rouge scores. We performed the pre-processing of the dataset, trained and evaluated the dataset on Google Colab, and tested locally to obtain Rouge scores. This way we extract the checkpoints from the training and evaluation for testing. Results of our Rouge score. The Rouge 1 F score gives us 0.388. Rouge 2 F1 score is 0.168 and Rouge L F1 score is 0.357. Now let's analyze the output. We used a TensorFlow frame, and this is an example of our article. From the reference summary, we see that it is a 3-sentence summary, and we obtain a very relative generated summary from our model.
Okay, and here are some future modeling exploration. And the first one is we can look some details about the sequence to sequence learning. And it's about training models to convert sequence from one domain to sequence in another domain, in which can be used for machine translation or question answering. And there are multiple ways to handle this task, and our team focus on the RNNs, and which can be seen as this graph. Mm, and these are some scripts about the sequence-to-sequence modeling. We first define an input sequence and precise it, and then we keep all the states from the encoder, and then set up the decoder using the encoder states as the initial state, and then set up the decoder to return full output sequence and to return internal states as well. And for the modeling part, we will define the model that will turn encoder input data and the decoder input data into decoder target data. And here is our method for the mean sequence to sequence model. And the results show that since the dataset is really huge, so I just choose 3 epochs, and we can say that the accuracy is not so high. So we then tried the sequence-to-sequence TensorFlow modeling, and the logic is the same. Like we define the encoding layer and define the process decoder input, and then define the decoding layer and use some TensorFlow features, and then to obtain the sequence-to-sequence model via TensorFlow. And we can see that the training accuracy improved a lot. And the third one, we tried sequence-to-sequence with glove modeling for more feature distribution and word embedding. But the results is not so well. And the second part, we can look details in the encoder-decoder RNNs. And it is an architecture developed for machine translations. In an extension of the encoder-decoder architecture is to provide a more expressive form of the encoded input sequence and allow the decoder to learn where to pay attention to the encoded input when generating each step of the output sequence, which has already been introduced before as an attention. And this architecture is as follows. For the encoder part, it's responsible for reading a source document and encoding it to an internal representation. And some commonly we will use bidirectional RNN like LSTMs, and we can also use word embedding to provide a distributed representation of words. And for the decoder, it is a language model responsible for generating each word in the output summary using the encoded representation of the source document. And it will give 2 sources of information. The first one is context vector, which is an encoded representation of the source document provided by the encoder. And the second one is generated sequence, which is a sequence of words already generated as a summary. And here are 3 models. And the first one is one-shot model, is to generate the entire output sequence in a one-shot manner. That is, the decoder will use the context vector alone to generate the output sequence, but it will add some pressure for the decoder. So we usually ignore this model. And the second one is a recursive model. This model is to develop a model that generates a single word forecast and call it recursively. That is, the decoder will use the context vector and the distributed representation of all words generated so far as input in order to generate the next word, as we can see in this graph. And also, we have implemented it in the next code scripts. Like we first build the input model and build a summary input model, and then we build a decoder model and tie it together with article, summary, and the word. And here are the results. And the last one is it's a model that the encoder will generate a context vector representation of the source document, and the document is fed to the decoder at each step of the generated output sequence. This allows the decoder to build up the same internal state as was used to generate the words in the output sequence, so that it is primed to generate the next word in the sequence. As we can show, the logic is like this graph, and also here is the code to implement that model, and here are the results. Okay, that's all.